Today we are going to talk about how physical properties emerge from molecular structure. But before we get too far down that path, I want to remind you about the kinetic molecular theory of matter, which gives a lot of the particle level basis for physical properties. Kinetic molecular theory has 5 assertions. 1. That matter is made up of tiny particles, atoms, ions, and molecules that have definite sizes that don't change. 2. The particles are in constant random motion and therefore possess kinetic energy. 3. The particles interact through attractive and repulsive forces and therefore possess potential energy. 4. Kinetic energy increases as temperature increases. And 5. Particles transfer energy through electrostatic collisions. That means they don't have to hit to collide. They just have to have the areas where repulsive forces exist hit each other to collide. Kinetic molecular theory then allows us to rethink our definitions of solids, liquids, and gases in terms of kinetic and potential energy. Kinetic energy generally pulls particles apart, making matter tend towards liquids and gases, whereas potential energy tends to hold molecules together, helping them tend towards solids. Potential energy takes 2 forms, intermolecular forces and pressure. The structure of molecules plays an important role in how strong its intermolecular forces are, and therefore what state it might be at any given temperature. There are 4 types of intermolecular forces, which again are sources of potential energy that hold molecules together. The strongest forces are ionic, followed by hydrogen bonding, followed by dipoles, and then finally London forces or van der Waal interactions. Ionic interactions are easy to recognize in a particle. If there is a permanent charge, it can have ionic interactions. Hydrogen bonding we generally see when there is a lone pair and a hydrogen bound to Nachtgeber, or nitrogen, oxygen, fluorine, chlorine, bromine, or iodine. And in organic chemistry, mostly that ends up just being nitrogen and oxygen. Sulfur maybe a little, but not appreciably. London or van der Waal interactions are always present and increase with size and contact between particles. Dipoles, however, need a little bit more effort to identify in a molecule, unlike the other forces. They require bonds that are polar and not symmetrical. If we want to understand dipoles in a molecule, we need to be able to think about geometry. We'll also see that later that geometry at any atom will control what types of interactions that atom can have based on spatial constraints, especially in Chapter 4. Valence shell electron pair repulsion theory gives us a way to assess the geometry at any atom fairly quickly. A primary aspect of valence shell electron pair repulsion theory is that we will view electrons as groups. No matter what type of bonds are present, each bond is always viewed as a single group. This means, since there will usually be 8 total electrons around an atom, the more double or triple bonds are present, the fewer groups that are around a molecule. We know that like charges repel, and all electrons are negatively charged. For this reason, groups will arrange themselves as far apart as possible, and we can quickly tell what shape the electron pair groups will take just by counting them. For example, a carbon dioxide only has 2 groups of electrons, double bonds to 2 oxygens from the carbon, and is therefore linear, whereas acetone has 2 single bonds to hydrogens, that's 2 of the groups, and 1 double bond to oxygen, so 3 total groups, and it will always be trigonal planar. So the number of groups determines geometry. What we are actually counting in each of these cases are electron pairs, which may include lone pairs. However, when we talk about molecular geometry, we are generally only referring to the arrangement of the atoms. Notice that the electrons influence the arrangement of the atoms. If we only have 2 atoms bonded to a molecule, like in the first row of this table, there are actually 3 different bond angles it may have depending on the number of lone pairs it also has. This differentiation is really important because linear molecules can be symmetric and have polar bonds canceling out, but bent molecules cannot. Carbon dioxide and water CO2 and H2O, both have polar bonds, but only H2O is polar as a molecule because carbon dioxide, CO2, is linear, while water, H2O, is bent. These structures show up biologically all over the place. The vast majority of our carbons are tetrahedral, but we can see important biological examples of most of these atomic arrangements in very common molecule types, like fatty acids, proteins, DNA, carbohydrates. The molecular geometry of an atom can also play a role in its reactivity. The molecule shown is cyclopropane. Cyclopropane consists only of carbons with 4 groups attached. Every one of them has 2 bonds to carbon and 2 to hydrogen. Normally, this would mean that every bond is 109.5 degrees, the maximum distance 4 groups can separate in 3 dimensions. But what are the interior angles of an equilateral triangle? Always 60 degrees. This difference in geometry costs the molecule a great deal of stability, and the molecule is much more reactive than it would be if it was not in a ring. Notice that on the structure of a tetrahedral molecule, I chose to draw the center carbon with one hydrogen as a bold wedge and the other as a dotted line. This is typically how we draw the 3-dimensional tetrahedral centers in 2 dimensions. Any bold wedges indicate that the atom on the wider end is closer to the viewer. A dotted line indicates that the bond is taking the atom away from the viewer. A helpful way of thinking about this center is that any 2 bonds around a tetrahedral atom will be a V. If you choose 2 bonds, the other 2 will also be another V, but facing in the opposite direction, shown here with the left V pointed down and the right V pointed up. The 2 V's will also be at a right angle to each other. By splitting up our thinking of a molecule, it makes us easier to see when the polarity of bonds cancels out in some cases. Here's an example of exactly that. Tetrachloromethane, the molecule shown here, can be split into 2 groups of bonds. The group on the left will have chlorines that pull electrons away from the carbon at exactly the same magnitude from left to right, but will be pulling in the same direction downward. The group on the right, on the other hand, will be pulling forward and back at exactly the same strength, but will be pulling overall in the same direction upward. We are left with a pull down on the left structure and a pull up on the right structure that also completely balance out. So tetrachloromethane, a molecule with only polar bonds, actually ends up being nonpolar. We can perform a similar analysis on other simple carbon and chlorine molecules. Notice that the hydrogens on one side of a dichloromethane, B, the center column in this diagram, are not able to balance out the chlorines, and a dipole exists on the molecule. We indicate this dipole with an arrow pointing toward the more negative side of the molecule, that's the chlorine side, and with a positive on the other end of the arrow. Notice also that this dipole is actually less than when there is only a single chlorine, like in column C, the one on the far right, because part of the pull towards a chlorine in dichloromethane is canceled out, top to bottom in the orientation that it's shown. Whereas in chloromethane, since there's only one chlorine, it pulls all in the same direction. Here are 5 examples of molecules. Start by drawing their Lewis structures, and then try to draw the correct molecular geometry. Pause this video to give yourself a chance to do it. After you finish, resume the video to check your work, and then pause again to try to assign the dipoles to the molecules, where appropriate. Bring these answers to class. So pause the video to try to draw out the structures. Here are the structures of the molecule drawn in 3 dimensions. Now try to assign dipoles to these and bring the answers to class. Now that we've talked about how to determine if there is a dipole on a molecule or around an atom, remember that this is a way of getting at one type of intermolecular force that may be present and can tell us a lot about physical properties like boiling point and melting point, where the stronger the intermolecular forces are, the higher the boiling point and melting point will be, because it takes more kinetic energy, higher temperature, to overcome the potential energy. We can also tell some about the solubility of a molecule in water because the more similar the average strength of intermolecular forces in a molecule are to water, the more soluble it is in water. This is really a rephrasing of like dissolves like. If intermolecular forces are similar on average, the molecules will be soluble. Take these two molecules as a case study. Sodium formate is dominated by ionic forces, which drives its boiling point and melting point really high. However, since ionic forces are stronger than hydrogen bonding, there is a limit to the amount of sodium formate that can dissolve in water. Formic acid, on the other hand, has weaker hydrogen bonding forces and with them much lower boiling point and melting point. But because formic acid's hydrogen bonding is more similar to water's, the two compounds can be mixed in any proportion. They're completely soluble. Here are another three examples. Ethanol on the top has the strongest interactions and the most similar to water, and so has a higher boiling point, a higher melting point, and a higher solubility in water. Ethanal, or acetaldehyde, because of its molecular geometry, has a stronger dipole than dimethyl ether on the bottom, and therefore has higher boiling points and higher melting point, and a greater solubility in water. These last three examples are of molecules that have London forces as their dominant interaction. There is not much difference between propene and propane, which both have very low boiling points and melting points, and are practically insoluble in water. Ethane, on the other hand, is smaller than the other two molecules. It doesn't have weaker forces, it just has fewer of them, which drops its boiling point drastically. But when you look at solubility, ethane is actually a little bit more soluble because it is smaller and has fewer of those weak interactions that displace water's strong interactions. So again, intermolecular forces are the potential energy that helps us to determine which state matter will occur in based on the kinetic molecular theory of matter. Solids will have strong intermolecular forces, gases will have weak intermolecular forces, and liquids will have intermolecular forces somewhere in between. To frame this once more in terms of kinetic molecular theory, we know that more charge means more potential energy, and closer charge means more potential energy. Ionic interactions give a full charge, and therefore give a high potential energy. Hydrogen is very small and is always held closely to other atoms, which gives more potential energy. Dipole interactions are going to give the most potential energy when they are the strongest, but tend to be weaker than hydrogen bonding and ionic interactions. And London forces are the weakest because any charge is always temporary. Many of our molecules are nonpolar, and London forces are the most important factor for their physical properties. London forces require a positive and negative charge to line up spontaneously on adjacent molecules. A few truths about this. Larger molecules are going to have more opportunity for this to happen. The London forces aren't ever going to be stronger, there are just going to be more of them. Molecules that are flatter are going to fit together better, and better contact between them allows for more and stronger forces between them. And more polarizable molecules have more electron mobility. This generally means that if we have big atoms like sulfur, chlorine, bromine, or iodine, they will have stronger London forces because they can move the electrons around more, whether or not they also have a dipole. To illustrate that size is an important factor for London forces, notice in the table below that the boiling point from methane to ethane to propane to butane to pentane consistently increases. So the longer that molecule gets, the higher that boiling point goes. To illustrate the idea of molecules that stack nicely have more forces, compare dimethyl propane to pentane. Both have the same formula, but pentane is much higher boiling because the chains can come closer together. Finally, to illustrate the difference that polarizability makes, notice how much higher boiling iodine is than chlorine, because iodine is that much bigger. Some recent science has played up intermolecular forces by generating molecules that are non-reactive organic ions that can be used as solvents for reactants. These solvents are easier to recover from a reaction, remember they're more polar than most organic products. You can usually dissolve them in water and can accelerate some types of reactions drastically. This allows for us to do reactions with less solvent and to recycle the solvent, which makes our chemistry that much greener. We put a lot of focus on boiling point and melting point, but let's circle back around to solubility. Remember, the one rule for solubility is like dissolves like. I would like this in your notes in at least size 96 font. This affects solubility on both ends. Magnesium oxide, Mg+2 and oxygen -2, has very strong ionic interactions because its ions have a plus or minus 2 charge and are fairly small and close together. Magnesium oxide is far too polar for water to dissolve it. Sodium chloride, on the other hand, now has weaker ionic interactions. They are now similar enough to water that we can get around 5 molar sodium chloride solutions at room temperature. So that's a pretty high solubility. When an ionic compound like sodium chloride or sodium formate dissolves in water, ionic interaction isn't displaced completely. We end up having the dipole of water lined up with the charge of the ions, which helps to balance some of the difference in energy. So notice that the negative end of the water molecule, the oxygen part, lines up with the sodium positive, or the positive end of water, the hydrogens, lines up with the oxygens on formate. In fact, most ions are going to end up with a bunch of solvent molecules arranging their dipoles. This is an important way that charge is stabilized in solution. So notice that in this formate that's on the left, there are 6 water molecules shown, each stabilizing the negative charge with its H+s. And in the sodium on the right, there are 6 water molecules, all stabilizing the sodium plus with a negative charge from the dipoles on water. Take these 2 molecules, acetone and water. Which intermolecular force is most important in each? Do you think it is similar enough to have them be soluble? Answer these questions for class. Ethanol and water both have hydrogen bonding, so they are similar. Ethanol and water can be mixed in any amount. Hexane and water are very different in intermolecular forces and will not dissolve at room temperature. Notice that while methanol, ethanol, and propanol are completely soluble in water, the average intermolecular force is becoming weaker with each additional carbon. Butanol has significantly weaker London forces than water's hydrogen bonding and becomes only partially soluble. By the time alcohols are 7 carbons long, they are no longer appreciably soluble in water. On the other hand, they actually start to become more soluble in solvents like hexanes. We often talk about functional groups as being hydrophobic, being afraid of water, or hydrophilic, loving water, to approximate their similarity to, and therefore solubility in water. More hydrophilic groups equals more soluble, and more hydrophobic groups equals less soluble. So hydrophobic groups include alkanes, alkenes, and alkynes, all of which have carbon bonds as their predominant functional group, and aromatics. Ethers, even though they have a dipole, the dipole is far too weak to displace the hydrogen bonding that we see in water. Hydrophilic groups, on the other hand, include carboxylates and carboxylic acids, ammonium groups and ammonia groups, amines. We have alcohols, which again are very similar to water because of the OH bond and the hydrogen bonding, amines, aldehydes, ketones, and esters and amides. The concept of like dissolves like can also be extended to how likely molecules are to interact, even if neither is the solvent. Notice that in the active site of an enzyme, every piece of the enzyme needs to be similar to the pieces of the substrate, what the enzyme works on, that it will touch. So we can see that where there's phosphate, we have polar groups that are interacting with the phosphate, and we have groups that are able to hydrogen bond with each of the available hydrogens for hydrogen bonding. An important application of the concepts that we've learned in this chapter is to be able to rank physical properties like melting point, boiling point, and solubility, given only structure. Remember, Physical properties are based on intermolecular forces. The strongest forces have the largest boiling point and melting point, and for solubility, the similarity of the average strength is more important than the overall strength. Whenever you encounter a physical properties ranking question, the main concept that's being tested is the identification of intermolecular forces. By way of example, we're going to try to rank these molecules from highest boiling to lowest together. First, let's go from left to right to identify the most important intermolecular forces in each molecule. Pause the video and try to do this for yourself first. If we look at A, we should see that A is going to be London force dominated because it's all nonpolar bonds. B has an O connected to an H, so we know it can hydrogen bond. C has two chlorines on the same side of the molecule, pulling in the same direction, so C will have a dipole. D again has no polar bonds, and so it's going to be dominated by London forces. E has two oxygens connected to hydrogens, both of which are able to hydrogen bond. F has only nonpolar bonds, and so must be London force dominated. And finally, G has two chlorines, but they pull in opposite directions, so it will also be dominated by hydrogen bonds. Now that we have all of the intermolecular forces identified, we can compare molecules in each group to see which molecules will be the strongest of that type of force. For hydrogen bonding, the strongest interaction dominating any of these molecules, the more open lone pairs and available hydrogens present, the stronger the force will be. E has two alcohols and will be tied together by stronger forces and be higher boiling than B. C will be the next highest boiling because it is the only molecule with a dipole as its dominant force. The last molecules are separated on strength of London forces. Working backwards, D should be the weakest because it's the smallest, followed by A. F has two CH3 groups, while G has two Cl groups. The Cl groups on G are more polarizable and arranged better for molecular contact, so G will be the higher boiling point than F, followed by A, and lastly D. In chemistry, we have two different types of polar solvents for reactions, and nonpolar solvents for other reactions. Polar protic solvents have a proton, H+, that is attached to something electronegative. These protons are readily available to solvate, or surround, any anions that might form in a reaction. So if you look on the right side, we see that all the H+ are surrounding that Cl- and helping to stabilize it. The electronegative atoms can also easily stabilize the cation by solvation, which you see on the left. All the oxygens are helping to stabilize the Na positive. A great example of this type of solvent is water, which is shown on the right. Dimethyl sulfoxide, which is shown below, is an example of a polar aprotic solvent, meaning there is no hydrogen attached to an electronegative atom, no hydrogen that can hydrogen bond. These solvents can still solvate a cation, so you can see on the left that we have the oxygens all coming into close contact with sodium positive. But they tend to solvate anions less effectively because their positive charge is less available, which you can see on the right. This has an impact on what reactions are possible in a given solvent. One straightforward example is that ionic compounds are much more soluble in polar protic solvents. Ionic compounds are much more soluble in polar protic solvents. A more meaningful example for organic chemistry is a reaction that may form a carbocation as an intermediate. So since a carbocation is positively charged, it's an ionic species, we know that we would need something to stabilize it. Ethanol, a polar protic solvent, can help to stabilize this carbocation and the anion, and so we can actually have this reaction occur. DMSO, an aprotic solvent, cannot stabilize the anion, so the cation will not form. Here are some of the most common polar protic solvents and polar aprotic solvents. The polar aprotic solvents are usually these specific molecules, so the three shown on the right. But think of the polar protic solvents as examples of functional groups, alcohols and carboxylic acids. We could have ethanol be a polar protic solvent, but we could also have methanol or propanol, and any sort of carboxylic acid can also function as a polar protic solvent. Some compounds are both appreciably polar on one end and nonpolar on the other end. Soaps are a great example of this. Traditional soaps are made from fatty acid salts, which have a carboxylate, the anion of a carboxylic acid, on one end and a long chain of carbons on the other. Liquid soaps are usually made from sodium dodecyl sulfate, which is also known as SDS, like in gel electrophoresis, or also known as sodium lauryl sulfate, as it's listed in ingredients like in shampoos and hand soaps. Soaps work because they form 3D structures called micelles that trap nonpolar molecules with the hydrophobic end of the soap molecule and draw them into water by exposing only the polar heads to water. So as you see below, the polar heads are all around the outside and can interact just fine with water, and the nonpolar sides are on the inside of the molecule and don't need to interact with water. You can see this as they surround a dirt or oil particle that's also nonpolar. It allows that nonpolar particle to now be soluble in polar water. Chylomicrons, which are particles responsible for moving fat from intestinal cells through the lymph system, function very similarly to micelles by trapping nonpolar fat molecules inside of a sphere of membrane lipids, which, like soap, are polar on one end, the end that interacts with water, and nonpolar on the other end, the inside end that traps the triglycerides, the fat molecules. One of the more interesting ways that we take advantage of intermolecular forces is by using crown ethers to dissolve ionic compounds in nonpolar solvents. A cation alone is pretty unstable, but a crown ether stabilizes the cation with multiple dipole interactions, leaving only the less polar outside of the crown ether to dissolve in the nonpolar solvent. You can see this below in the example with potassium. All the oxygens are pointed towards the potassium, and all the carbons are on the outside. Crown ethers can be adjusted in size for different cations too. When crown ethers stabilize cations, they make the anions available for reactions. The structure around atoms and the dipoles that result clearly have a really important impact on many aspects of chemistry.